last time we considered some of the passive devices, which are solar cookers, solar ponds, solar desalination or solar stills. Now, as a part and parcel of the building, many of the time the passive architecture is included either to heat the building in cold climates or to provide a little bit of cooling, so that directly the sun will not enter into the building. So, this we shall call it passive architecture, which will include overhangs and wing walls. This, all of us have seen it, possibly we may not be knowing the name of it, but then I shall tell you it is very simple. And there can be a direct gain window. It is just nothing but a window, and if you close it, the solar radiation entering into the window will not escape after heating the body inside because of the longer wavelength radiation. And then you may or set up convective loops to keep the room or the enclosure warmer, and thermal storage walls, which will accumulate the energy during the daytime and release or emit or convect in the evening time, so that there is a comfort condition of higher temperature, particularly useful in colder climates. And then you have got roof ponds, which will keep the room or the underneath floor much cooler. Then you have got attached greenhouses. In fact, many of them work on the principle of the greenhouse. The solar radiation entering into the greenhouse through the glasses will be re-emitted at a longer wavelength. Consequently, it will not escape, and the window glass has the property that it allows the solar radiation at a lower wavelength, but shall not allow the longer wavelength radiation to escape. Hence, the enclosure will be hotter or warmer. So, if you attach it to a house, then in the evening time or the night time, the heat emitted or released by the greenhouse from the greenhouse will warm up the house. Then heat transfer control and heat storage, these are general terminology that are used in and very specific systems would be, one of them is a trombe wall, and then solar roof ponds and thermosiphoning air collector. And you can see Anderson Mitchell this is according to my number, it is mentioned above the design of the common systems such as trombe wall. Trombe wall is nothing but a hollow wall with something like this. If this is the wall and a hollow space is there, cold air gets warmed up and goes into the room and hotter. This is a absorbing surface. So, basically it is a sort of hollow wall through which air can be circulated, which will keep the room warmer. Then you have what is very popularly called green houses. A typical arrangement could be something like this with certain slanted roof, and you may have an exhaust fan over here, and depending upon the purpose you need, you may have plants, and then maybe storage drums of water like this, and the whole thing may be attached to a house. That is what we had earlier in mind. Or this is glass, this is glass. It is debatable and depends upon the direction. Still, you do not lose anything by having a glass on all sides, including this particular side. Okay. Now, if you have a situation like this, the solar radiation entering sun's rays cannot go back, because of this will be emitted at a longer wavelength compared to the radiation at which it is entering, 0 to 4 microns, typically the solar radiation, right. So, this gets warmed up and this drum of water gets warmed up, and in the night it releases heat, and you may divert this fan into the house, which will keep the house warmer. In addition, in winter the plants, they can survive with a temperature of 20 C or 30 C, right, instead of sub-zero temperatures. And in general, these greenhouses, you can use it to protect the plants or survive, or maybe even for drying and space heating supplement. Okay. So, plants we covered, space heating supplement also we have mentioned. What about this drying? In case you have a like coffee, for example, or even tea, if you have a greenhouse, and of course we shall use the fan to remove the hotter humid air, and there will be a layer of Arabica or Robusta coffee. One can think of a number of other arrangements. If you are tea leaves, the advantage is, if typically the drying is 2 to 3 times faster. That is, compared to open sun drying, if you do it in the greenhouse, it will be 3 times faster or 2 times faster. And if that is so, alternately you need 1/3 the area. So, in a coffee plantation, if you are using 20 acres of coffee for the land, you may require, let us say, 2 acres for drying, then I need only 2 by 3 or less than 1 acre for drying if I use it in the form of a greenhouse. Consequently, the remaining 2 acres can be released for cultivation of the coffee, which will in general will be much more paying than whatever you spent on the greenhouse for the drying purpose. So, this is one particular area where you have got a very attractive solar application without much investment. Then you can have a conventional solar dryer, which may be active or passive. This is particularly important because the investments particularly in the case of passive systems, are lower compared to active systems, and you have got a number of cash crops which may be coffee, tea, cardamom, cinnamon, black pepper, etc. And if you have got pharmaceuticals, tablets, and a chemical, lot of sludge. After the process, you may have a colloidal semi-solid, semi-liquid type of waste material that is being discharged from many chemical industries and pharmaceutical industries. Then in addition, you may have resins and fish, etc., and including even maybe even potato chips. One should be careful that it should dry and not cook. This can happen if the moisture is a little higher and the temperature is a little higher. Now, these are particularly mentioned, all these to be dried say less than 60 degrees C. The reason being, if the temperature is more than 60 degrees, oils and flavor contained in these things may be lost. So, you do not want to do it too fast by using a higher temperature, but you would like to do it faster than what you can achieve under natural conditions in open sun drying. And open sun drying has the other disadvantage rather, there may be contamination coming from various sources, and if there is a sudden shower, the product almost dry may get wet, will get wet, and may lead to degradation of the quality, if not completely spoiled. So, this is of course an age old method, is sun drying, and particularly is a crude method which may yield a poor quality product. And macroorganisms can be growing, and use of appropriate solar dryers may remove some of these disadvantages of sun drying, particularly from the point of view of quality. So, even if you spend a little higher amount, the quality will be better and also faster. Consequently, if your prime agricultural land which is devoted for drying, even if half of it is released, the payback will be quite attractive. So, we may talk about a solar hot air drying system. Invariably, they use, whether be it a direct gain window or be it a trombe wall or a greenhouse, essentially it is a air based system. And in fact, typically it is called for fish drying in the particularly eastern part of India, and can be useful for any product of comparable size. Okay, or you can modify the tray design. For example, if you take a simple cabinet type of dryer, which I may show like this, bottom is insulated, there is a plate, I will let in air in, there may be a fan, air out, and this is sort of an absorber, just like the solar still, except there is no water, and the entire thing, there may be a grill or a or what you call mesh, and I may hang resins or grapes which are to be dried, and one can suitably choose the height of this mesh above the absorber depending upon the length of the bunch of the grapes, or you can alternately put on this either coffee seeds or cinnamon or any of these products, and appropriately may or may not have necessarily the grill. Okay. So, you can easily modify if you take this is essentially, this is glass again, of course you can have glass. This is to let the cold air in, passes through the spaces, carries the moisture and gets out through the air duct. Okay. And in addition to direct heating or direct drying from the top surface. So, if you close it completely, there will be an accumulation of moisture. It may start working like a solar still rather than a solar dryer. So, this is a cabinet type. Basically, they are all greenhouse effect. So, if you have a forced convection, will be faster obviously, but this passive is faster 2 to 3 times the open sun drying. The fringe benefits are contamination free. So, I have whatever I have described, it could be a cabinet type of dryer with if I can see, you can see on this, these may be glass roofs, this glass, and various arrangements can be thought of for putting the product. So, this is essentially a cabinet type of dryer which I have shown one side of it, and shelf type dryer with flat plate solar collector heating system. Now, you may have a circulation by a blower. Strictly these are not this is not a passive device, but I have included in this because of as an application of drying. So, you have a solar collector and you may have here a conventional dryer. If you like, I would like to, this is your solar collector through which air is being circulated. This goes to a cabinet dryer, and I may have a number of trays and the air goes up, goes out. So, in that process, of course, you can shuffle these trays from bottom to top and top to bottom, so that there is a uniform drying at the end of a certain period. So, basically this greenhouse type of solar dryer, if we now summarize, though we have understood the idea behind it, solar dryer, greenhouse type, basically passive. It's a contains a black painted chamber, and a transparent cover, it may be glass or plastic. Oh, this about plastic materials in general is desirable because of less chance of breaking. Owing to thermal expansion or contraction during day and the night. But the disadvantage is, in general, plastics are not UV stable. The ultraviolet radiation, though 2% or 4%, that will make the plastics unstable, and after a while they lose their color, they lose their rigidity, they simply break. In fact, our common experience shows one fine morning when you are picking up a bucket of water, that bucket breaks down after 5 years or 4 years of service, and you can't fathom the reason why it happens, but that is basically the UV instability, and particularly those things that are used outside, exposed to the sun, are more liable for this sort of a damage rather than the ones that are completely used inside the house. And transparent cover, which can be glass or plastic, and then 3, of course, the trays, the size and stacking depending upon the size of the product to be dried. That's what I have already. And air entry ports for air entry. This is not so much to heat the air and use the hot air to dry, but this is essentially to carry away the moisture when once drying has started place. So, for example, if you take a food product, so the moisture in that will come to the forefront or the skin, then diffuses out. So, this needs to be carried out. Now, the drying time, in addition to the total moisture, will be dependent upon what type of a skin the particular vegetable or the fruit has. For example, if you take coconut, you can't dry the coconut so easily, right? And if you take onion, it's relatively more easy. And if you peel off the outer layer, it will be even more easy, because the outermost layer will have less porosity and it will not allow the moisture to diffuse out. Okay, these are the tricks. As a matter of fact, you, for example, you take potato, if you peel it off and cut it, it will be more easy to dry. If you do not peel it, then that skin will be a quite resistant one for moisture diffusion. Possibly it will cook inside rather than dry. So, the dryer is aligned east-west lengthwise and about 5 meters above the ground. So, the air temperature is about 20 to 30 degrees centigrade above the ambient. If there are no rains and at least 11 to 3 p.m. So, that corresponds to typically 40 to 65 degrees in tropical climates, which is rather ideal for drying of resins, coffee, tea, black pepper, etc. The higher temperature is not desired because it will take away the oil in that or make them sort of soft by semi cooking rather than only drying. So, greenhouse and trombe wall which are shown here, which we have already covered or discussed about. Yes, the shading is an important aspect, particularly in tropical climates. To prevent sun entering through a window, and in the colder climates or season, to let sun enter. Fortunately, the sun's position favors this. If I consider a window, let us say this is the window in the side view, and this is the sort of a you will see often what you call a overhang. So, if the sun is somewhere here right above, this will be shaded or shadowed if you like it. This may be summer because sun is right up, it will cast a longer shadow on the window. And if you see the same thing in winter, sun may be somewhere over here and it will cast a small shaded or shadowed. So, it will let in the sun in winter, whereas it prevented so much of sun to enter during summer. The positions of the sun, at least in the northern hemisphere, as shown here, it is pretty low in winter months or declination negative in general, and in summer months it will be high up almost at the right at noon time right above your head. So, consequently casts a longer shadow shading the window. So, this is not just for protection against the rain, and you have a overhang to provide additional heating in the cold climate or not allow the sun, if not directly cool it, indirectly let it be cooler by not allowing the sun to enter the room. And you can have, if you see some of the buildings, which you may think that it is sort of an architectural beauty, but really they are functional. You have a wing wall, this may be a window or opening, just like the overhang projection for the window. These are on the sides, so that if this is south and if this is east and this is west, these wing walls will prevent sun's rays entering the window or the opening in the morning time from this wing wall, and in the afternoon by this wing wall. So, consequently, they will project some kind of a box type of structure which will not allow the sun to enter. And if you combine it with a overhang also, and it can be completely shaded as your desire, if that is the. So, there are quite a few relevant literature is in 57 and 58 on the overhangs and the wing walls, but the basic things I shall cover over here. So, as we said that now the direct gain window so, whether there is overhang or not, there will be a certain amount of solar radiation entering. Suppose the objective is heating. Your TA may be 2 degrees C, and you obviously want T room to be approximately, let us say, 20 degrees C, right. So, you have got let the sun enter to heat the room up to 20 degrees C through a direct gain window. If you look at your solar radiation distribution, something like this, IT, this is minus omega s, this is plus omega s, this IC, just like in the utilizability, will correspond to 20 degrees C. So, I will calculate my non-dimensional or dimensional critical radiation level corresponding to a temperature of 20 degrees C. Now, when we want the energy delivered to be T minimum greater than or equal to 20 degrees C in your phi bar or so called phi bar F chart method, then the radiation above the critical level is useful. In the case of a direct gain window, this is IC corresponding to T minimum, let us say 20 C, this not utilizable. In other words, when the radiation is above this critical level, it heats the room beyond 20 degrees C, which we do not want. So, my unutilizability is 1 minus utilizability. On any time scale, if phi is hourly utilizability or for a day or for a monthly average day, then 1 minus phi will be the unutilizability. In other words, the solar radiation above a certain level is not useful in heating my room. So, whatever we try to do as far as a useful energy gain is concerned, with this direct gain windows, you calculate utilizability as if it is a collector supplying at T minimum of 20 degrees C, and that utilizability 1 minus of that is the one actually that is utilizable, and the above one is unutilizable. You do not want to heat it up beyond the requirement. So, I have given the definition here. Unutilizability may be defined as the ratio of solar radiation below a certain critical level to the total solar radiation. This critical level, as has been defined earlier, is the solar radiation level needed to maintain the room at the comfort level. So, the radiation above that level is not utilizable. So, I may call it phi unutilizable equal to 1 minus phi utilizable. Similarly, I can extend it to different time scales. So, phi bar unutilizable will be 1 minus phi bar. So, from overhangs and shading and a direct gain, so we come to this unutilizability. So, you calculate as usual your utilizability, and 1 minus phi bar will be unutilizable multiplied by your HT will be the energy that will be going into heating the room to the desired level of, let us say, 20 C. Now, the shading factor. So, we have seen if you have got a window, let us for the simplicity assume that it is facing south, and we have got overhang of certain right flush with the top of the window, and that will cast a shadow like this. Right. So, if I want to make it clear to you, I will not show the overhang, but I will show the different types of shadows that it can make. So, you may have a shadow something like this, out of which this is the area of the window that is shaded, right? Or I may have, for example, a perfect rectangle. For example, if it is solar noon time facing south, or the corresponding gamma and the corresponding time, you will have a simple rectangle. If the overhang is equal to the width of the window, I will just have a rectangular thing. But this could be the morning, and I may have forenoon rather, not morning. This may be afternoon, and this may be forenoon. So, if this is east, this is west. Okay. Now, the whole idea is to calculate what is the solar radiation entering through the window with the shadow, okay, shaded by the wing wall. And if it is equal to the width of the window, then I can have a situation like this where a sort of trapezium is shaded, and a complete rectangle could be shaded if it is exactly in the facing the south, facing the sun, or it could be a degenerate case of like the ones I have shown here or here, depending upon whether it is forenoon or the afternoon. And you can have still further degenerate cases. I am showing only the shadow, and this can come right up to here and go. So, this may be the shaded area, right, and still it may do little more than this. It will not end here, but it may be like this. Okay. What we are trying to say is this edge may be on the edge of the window or may be below, beyond the window. So, now the problem is, what is the area shaded? So, that depends upon this or this, and in the case of a complete rectangle, no problem, width multiplied by the thickness, but we need to know whether the shadow belongs to a triangle category just ending at the edge of the window or beyond the window, or a rectangle or some sort of a trapezium like the ones we have shown earlier. So, now the issue lies that we have calculated solar radiation falling on different surfaces, both shorter and long term. Now, the question is, what is the solar radiation received by a, say, window with a overhang? It does not have to be a window, it can be any surface which is shaded by sort of a overhang. So, one can, we do have results for this accurate description of the shadow in the Rahman or in available 58 reference, which I shall give at the end of this lecture series. So, we define what is called a shading factor. This is the ratio of the lit area of the surface to the total area. So, with reference to the window, if I am looking directly at the window standing in front of it, let us say this is my shadow. So, the whole thing is AW, window area, and this is let me see, okay. If you have got this to be I do not know what notation I used, AW will be H into W, and this crosses area is the A lit. that means it is lighted to some extent and this part is shadowed. So, that is what the shading factor concept, and I think the one without the lines is the overhang and this one is the shadow. So, this at any instant the shading factor is A lit by AW. So, if there is no shading, A lit is 0, consequently A lit is equal to AW, sorry. So, Fi will be equal to 1. And Fi will be equal to 0 if A lit equal to 0, which means completely shaded. So, initially it was confusing even to me. The shading factor is defined not in terms of the shaded area, but in terms of the area that is lit still. So, A lit by AW is the shading factor, and if A lit is equal to AW, there is no shade, that means it will be equal to 1 when there is no shading at all, and it will be equal to 0 when A lit is 0, and A lit will be 0 means that the window is completely shadowed. So, if you have got this Fi on an instantaneous basis, A lit keeps on changing just like the solar radiation and also because of the position of the sun. So, if I want a longer term Fi bar, I should use this, borrowing a leaf from the calculation of Rb bar. This in general will be omega Sr to omega Ss, omega Sr to omega Ss. So, the numerator represents the solar radiation falling on the collector, window surface, and a part being shadowed, and this is the radiation that the window would have received if there is no shading at all. So, just like you can compromise under extra directional conditions will be integral. Of course, I will use the intensity G0 Rb Fi d omega upon G0 Rb d omega. Again omega Sr to omega Ss. So, the total radiation that will be falling on the collector surface if there is no shade compared to that if there is a shade with a shading factor of Fi, and this Fi is a function of omega in addition to, of course, phi, beta, gamma, delta. So, it is a function of time, and if I can have an algorithm for Fi, G0 is analytical, cos Rb is your original cos theta by cos theta z. We may or may not be able to, this can be integrated, this we know it, and we may or may not be able to do an analytical integration for every case, but nevertheless it is average value over a time period, a day or the monthly average day or between T1 and T2 during a day will be G0 and the instantaneous RB multiplied by the instantaneous Fi if I have an analytical expression for this upon the radiation falling had the solar window had not been shaded. Now, you can go through the same logic Fi bar 0 approximately equal to Fi, I mean rather reasonably accepted because of error being committed both in the numerator and the denominator, or and your Kt is reasonably uniform. If it is equal to 1, this relation is exact, but what we also proved earlier was that, well, this relation is not too bad even though it is evaluated under the extraterrestrial conditions, because you are committing a mistake both in the numerator and the denominator, and on top of it, for the as far as shading is concerned, both numerator and the denominator are integrated from omega SR to omega SS. Unlike in the case of our flat plate collector solar radiation received, the integration is between omega SR to omega SS in the tilted radiation, whereas and twice of 0 to omega S in the denominator, and that could make a difference in the time element of the numerator and the denominator. But as far as the shading factor is concerned, both of them are during the time period that they receive the radiation. Okay. If the radiation is not received by the solar collector, obviously there is no point in calculating the shading factor. We shall continue it tomorrow because a lot of approximations have to be made. However, a large number of tables or graphical results are available, but here I am essentially trying to tell the concept that this is one order of magnitude little more complicated than RB bar. Thank you.